Good afternoon, everyone. I am going to show you the implementation of our paper breaking cryptographic implementation using deep learning techniques. For the coding part, I am using a Python package called SCAAML, which stands for Side Channel Attack Assisted with Machine Learning. It was written in Python and runs on top of TensorFlow 2.0 version and developed by the Google security and privacy team. And it wasn't a official product of Google, and to download this package you can go through this GitHub link. And now let's jump into the execution part. And for the data set we are using the power consumption traces of a device which were encrypted using tiny AES key. And what is tiny AES? Tiny AES is a Python package which gives encryption and decryption methods in the AES family. And for this example, we are using the AES 128-bit encryption, and this was the configuration file, and these are the power traces data sets, the training and the test one. And this configuration file where we will give all the details like what was the algorithm we are using and the device name and the algorithm which was used to encrypt and the version and the attack points which were previously explained in slides. And as we are using 128 bits, so the number of bytes are 16, so it was 0 to 15, which is 16 bytes, and the max trace length and the number of threads and all those details. And the parameters for the activation function, we are using ReLU function, and the learning rates are here. And now let's see the coding part. The coding part was a very big one, so I just now ran everything, and I'm just showing the explaining the coding part. And here I am importing the required packages and the setup being the environment, which are the details extracted from the or taken from the configuration file, and the available models. As we are, the attack points are 3, so they are the 3 attack points, and number of bytes we have to recover is 16, so they are 16. And the dataset path as mentioned previously from here. And for the single byte recovery, this was the code, and the number of traces we are using were 10. The 4 traces are enough for the complete recovery, but for the best case we are using 10 traces, and the bytes was recovered successfully. And this was the process, like it will take a bit of time. And the accuracy, when we are taking or the one trace, the accuracy is 0.45% only. And byte recovery efficiency, this was the graph I am mentioning before, like when we are taking number of traces greater than 4, the recovery is constant and it was 100%. And you can see the graph, like with respect to 1 it was 45, and with respect to 2 it was 90, with respect to 4 it was 100. And the metrics calculation and everything. And here we can see the cumulative result, like minimum traces is 1 and the accuracy is 42.6, and the maximum traces to recover 100% of key was 4, and it was the cumulative score. And the full recovery of all the bytes, and this was the part for that. And we are guessing the real value and their recovery key. Here you can see the recovery key and the real key, and it was just 100%. This was all the execution part. Voila, we got the real part and the recovered part. So we successfully recovered the key which was encrypted. Thank you.